Hi, in this video, we're going to take a look at multinomial models within Bayesian statistics. Okay, so our outcome is a random categorical outcome. So when I say categorical, this could be something like left or right. This could be something like, let's say, um, yeah, maybe the state that a person's born in, or the country that they're born in, or their political affiliation. Any categorical level that you could possibly imagine is something that we could have. Another one, maybe, what company do they have for their auto insurance? There are tons and tons and tons of categorical outcomes that come up all over the place, and we need statistics to analyze them. And overwhelmingly, we use the multinomial model for this. Now, in multinomial, we have a fixed number of possible outcomes. So, for example, if we're saying the state that an American citizen is born in, I'm going to disregard territories for the moment, but then there's 50 possible combinations. So if I have a probability distribution on that, I have to have 50 parameters, a parameter for each possible state, all the way from Alabama to Wyoming. Okay. So what we want to be able to do, we want to be able to incorporate prior belief, prior understanding into a situation to get a better statistical model. Right now, whenever I'm doing statistics, if I'm going to be using Bayesian statistics, the best use for that, in my opinion, my biased opinion, is that when we're going to use the additional information that the Bayesian model gives us, our stakeholders wants to, or I'm in a small data situation. In my opinion, those are the best cases for Bayesian statistics. Bayesian models are more complicated. So if I have sufficient data, I personally don't go with them first and foremost, but there are specific cases where they are very, very powerful and very, very useful. And so they have a good place in the world of statistics, and we need this as a tool in our tool belt. All right, so I'm going to be modifying what we're talking about from Jim Albert's book on Bayesian computations with R. Here's his website, Bayesball, GitHub, and here's where you can buy the textbook. Also, students at the University of Central Florida can download the textbook for free as a PDF through the university's library. Um, all right, so let's get down to it. Boom, let's do this. All right, so let's talk about multinomial models. So the example we're going to run through is for political voting. All right, so for this, we're going to go back to 1988, the first Bush president election versus Dukakis. Okay, so we've got some data, and so CBS News ran a survey, and in that survey, there were 727 who were supporting the one that would ultimately win, the vice president at the time, 583 supporting Michael Dukakis, and 137 supporting either a third party candidate or no opinion, no preference whatsoever. All right, so when I talk to each individual person in the surveying process, there's three possible outcomes. Well, you know what? I'm going to take this as a multinomial problem, and where I've got, these, different levels. First level is going to be the Republican candidate. Second level is Dukakis. And the third is all other possibilities. So third party candidates or no opinion whatsoever. And so we have just under 1,500 as our observed data. And for our multinomial, let's go ahead and just say that these thetas are the underlying true proportions that American voters support each of the candidates. Remember, when I go out and do a survey, I don't know the actual values of this. I'm trying to estimate them. All right, so one thing that we can do is that we can assign a uniform prior and then get the posterior proportionals. Okay, so what's going on here is that each of these are a probability between 0 and 1, and the whole thing is a probability vector. So the probability of it getting exactly this result, these three numbers, is going to be the respective probability to the power of its counts. And so how would I actually get this? Well, what's going to end up happening is I walk up to the first person and ask them. And so that's going to be, I'm going to put in a 1 over the candidate that they go for, a 0 above all the other candidates. And then I'm going to go up to the second and do exactly the same thing. A 1 to the power is going to be the exponent of the probability that they're for, and a 0 for the other ones. And then we're going to multiply them all together because of how this works out. Multiplication of exponentials, same as summations. All those ones add up, and boom, we're going to simplify down to here. So this is the likelihood of observing exactly these values when I go to my counts. Okay, so now that is like our max, that we could use this for maximum likelihood estimate if we wanted to go like the frequentist approach. But we want to do Bayesian statistics. Okay, so what we're going to do is we're going to assume a uniform prior. And so let's say I have no knowledge, no prior information about American politics. I don't have any understanding of anything. So I'm just going to put a 1 across the board. All right, it's going to work out because of conjugate prior. My Bayesian statistic, my posterior distribution is I'm just going to end up effectively adding 1 to each of the counts off of this. Easy peasy, lemon squeezy, like that. And now, in kind of a contradiction, we know that it's going to be between the two major candidates. It's just been that way for a while. So, you know what? We're going to focus on the difference between the Republican and the Democrat candidate. And we want to reach a conclusion on who's going to win so we can make a prediction and say, hey, we called it, you should trust us in the future. All right. So R lacks a Dirichlet distribution random number generator. In fact, what I'm doing when I do this addition on the count aspect is I'm taking the observed data counts plus the parameter in my prior distribution and adding those on here. And the parameters of the distribution are the parameters of a Dirichlet distribution. The Dirichlet distribution is a continuous probability distribution for probability vectors. Okay. Now, to my knowledge, this is the only standard distribution for a probability vector. You could make infinitely many, but the mathematics works out very nicely for Dirichlet. And since the mathematics works out so well for Dirichlet, we pretty much just always use Dirichlet for everything, anytime it's a probability vector. All right, so although R lacks a Dirichlet random number generator, a simulation is pretty easy with gamma variables. All right, so if I have a gamma random variable with alpha and any beta for the gamma distribution, then the vector of rescaled values to be a probability vector will be Dirichlet alpha 1, alpha 2, alpha 3. Now with this, the gamma has to be the same beta value, the same scale value for all 3 of the individual ones. So I've got 3 gamma random variables that when rescaled gives me a probability vector, and that's how I get my Dirichlet distribution. It's critical that each of these have the same scale parameters, but they can have different shape parameters on this. Okay, so in my prior, I picked 1, 1, 1 as the Dirichlet parameter value. So here, alpha 1 is 1, alpha 2 is 1, alpha 3 is 1. Because I don't have any prior knowledge of American politics, I went ahead and just put them all equal across the board. And I picked small values because I don't have a lot of confidence in what I'm calling out as my prior. If I would have gone with really, really, really big numbers, let's say instead of 1, I did 1,000,000 for each of these, I would be very confident in what I believe in my prior. Okay, so let's go through. And here's my alpha 1, alpha 2, alpha 3 for my posterior distribution. So I'm using conjugate prior. Here's my data. Here's my prior distribution value. Add them together. That's my posterior alpha 1. Take my data, add my prior alpha 2. That's my posterior alpha 2. Take my data, add my prior alpha 3 together. That gives me my posterior alpha 3. And so now I can go through and start generating things nicely. All right, so now let's take a look at what we've got. I'm going to make this a little bit smaller so we can see the entire plot. And we can see that, practically speaking, the entire distribution is positive. All right, so this is strong evidence for Bush winning the election, which, lo and behold, he did. Okay. So it's just an easy way for us to reach a conclusion using statistics. Now let's go a little bit deeper into the Dirichlet distribution as our conjugate prior. Let's take advantage of the Dirichlet distribution to get a prior that better reflects politics. All right, so in the United States, practically speaking, when it comes to presidential elections, there are only two parties. Yeah, you can argue that there are others, but there's two parties, at least on the ballot, the ones that are actually going to get the votes. And practically speaking, it's 50-50, but there are a few people who vote otherwise. So what I want to do, I want to have nearly 50-50 on Republican and Democrat. And then I want single digit percentage for all other candidates and the ones who are just going to go to the ballot box and not enter anything for president. Okay, so remember the Dirichlet distribution is a continuous distribution for probability vectors. We can view these probability vectors as rescaled gamma distribution vectors that where the gamma distribution all has the same scale parameters. Each parameter of the Dirichlet distribution corresponds to the shape parameter of its corresponding entry of the probability vector. All right, so here, if this is that gamma random variable, I've got a different shape parameter for each one, potentially different each time, and then the scale is going to be the same every single time. If I have this random variable for my x's, then the rescaled probability vector from the x's is going to be Dirichlet distribution, and the alphas are going to be the parameter values. Okay, for us, there's only 3 entries because we're dealing with politics. But you can see that this would work for any length of vectors. I could do it with 50 states if I wanted. I'd have a length of 50 probability vector. Now, marginally, each entry in the Dirichlet distribution is going to be a beta distribution. So if I look at probability vectors from a Dirichlet distribution, and I only look at one entry, let's say only look at entry 3, then it's going to end up that the individual entry that I have in that position is going to be a beta distribution with a corresponding parameter from the Dirichlet distribution or the gamma distribution, however you want to look at it, is going to be the first parameter of beta, and then everything else added up is going to end up being the second parameter value. And the expected probability vector is the parameter vector rescaled to be a probability vector. So if I take all of these guys and I rescale them to be a probability vector, that will in fact give me the expected value of my prior distribution. Okay, now something else about this, if I have a very low variance prior, I'm saying I have a lot of confidence in my prior. If I have a high variance prior, I'm allowing the data to speak. And whenever we do Bayesian statistics, we have to do a balancing act in this. Okay, so when I look at this, I'm going to say, you know what? I think 49% Republican, 49 Democrat, 2% all others. In my opinion, that's about right. Okay, maybe you've got something different. I won't argue with you. Okay, so what I'm going to do, I'm going to take the parameter values that I have here, and I'm going to add them. So here are the parameter values. I'm going to add them to the counts that I have for Republican, Democrat, and other. And now let's do my Bayesian statistics. Let's take a look at what we get. Okay, so we end up getting similar results. We can see that the distribution is a little bit shifted to the left, but overall we reach the same conclusion. We see that this difference between the parameter estimates as a distribution is, practically speaking, 100% positive, which means that this is strong evidence that Bush is going to win. Okay, so now let's do something nuts. Let's go crazy. Remember, I said if I have a low variance, I'm putting a lot of emphasis on my prior distribution. Okay, to do that, in this situation, I increase my prior parameter values. So let's kick it up. Let's go through and multiply my 3 parameter values by 100. All right. So I've got 4,900, 4,900, and 200 as my parameter values. Now check out what happens next. All right, look at that. Look at that. That distribution is spot on 0, right? It is on top of 0. What this is showing us is that I have put so much faith, so much emphasis on my prior distribution that my posterior distribution ignores my observed data. Since it ignores my observed data, what was the point of doing statistics in the first place? All right, so this is an example of a prior distribution biasing the outcome. So this isn't a good result, honestly. We always want to do a balancing act. We want our prior to be informative, but not so informative that it drowns out the data that I have. All right, now let's look at another example. Let's go in the opposite direction. Now I'm going to drop the size of the parameters, but notice I still have the same proportions, right? I have the same proportions, practically 50-50 with a small little bit on the end. Let's see what happens. All right, now this looks a lot like my original data. All right, so with this, what has happened is that my data has such a high variance aspect to it that it really didn't get much input into the posterior model. And so this sets it up so that my data can speak loudly. All right, so my opinion, the first one that I showed, the 49-49-2, would be a good choice. Now, if I wanted to make sure that I don't bias things and my data gets to speak clearly, that 0.49, 0.49, 0.02, the last one, would be a good choice. But realize that that prior doesn't really get to speak. It doesn't get to say anything. It doesn't have much of an impact. So why am I bothering with Bayesian statistics? We want to find that balance point when we're doing our analysis. All right, I hope you found this video helpful and interesting. So remember, life is short. Do math.